Now I'll begin with the introduction to multicollinearity problem. And the general problem is when the number of predictors P approaches or exceeds the sample size N, coefficients that are estimated using traditional regression techniques become unstable or cannot be uniquely estimated due to multicollinearity, singularity of the covariance matrix. Now, often we get very high R-squared, but that indicates good in-sample prediction. But since that's often due to overfitting, it will not generalize to new cases. So if you try to take that model, apply it to new cases, it doesn't validate. The R-squared goes way down. Okay, and the problem is due to correlation among the predictors that steadily increases as P approaches the sample size. And if the number of predictors is equal to the sample size, any predictor can be expressed as an exact linear combination of the other predictors. That's perfect multicollinearity. And this occurs even if those predictors are totally uncorrelated in the true population. That is, in the population, they may be totally uncorrelated. You take a sample, though, as P approaches N, this problem occurs. So any predictor can be expressed as an exact linear combination of the other predictors, even if they're totally independent in the population, if, in fact, the sample size is equal to the number of predictors. Traditional methods cannot handle this problem. Okay, so just to, I'm assuming that everybody's familiar with ordinary least squares regression. So just to get some notation down, we have y as the dependent variable. I refers to the case. Here we have n cases. We have an intercept, regression coefficients, beta 1, beta 2, beta p for the p predictors, and an error term. The assumption made in linear regression is that the error term is normally distributed with zero mean for each set of values for the x's. In other words, for a given individual I with values for the x's x, we take the prediction we use is the expected value, so we predict at the mean. If we take the expected value of this equation here for a given x, since we assume that the error term has an expected value of 0 for given values of x, that drops out. And we get the prediction is equal to this. So if we get unbiased predictions for the betas, which is obtained by least squares, then we have an unbiased prediction for y. Okay, the problem is not due to being biased. Least squares gives unbiased predictions. The problem due to when we have a lot of correlation between the x's is associated with the variance of the prediction, which also manifests itself in high standard errors for the regression coefficients. Now, if we look at the regression coefficients, B is equal to x prime x inverse x prime y, familiar formula. X has dimension n by p, number of cases by number of predictors. And we assume, this is the least squares assumption, we assume that no exact linear relationships among the p predictors are in the model. Otherwise, x prime x is singular, and we cannot do least squares x estimation because we cannot invert x prime x inverse. So that's the case of perfect singularity, perfect collinearity. But the problem that we'll be talking about here is near collinearity, which means that near singularity of x prime x. In that case, we get imprecise, unstable parameter estimates. Now, define the tolerance in a minute, but if that's small for any predictor, or if, again, as the number of predictors approaches the sample size, n minus p is small, then small data changes produce wide swings in the parameter estimates and large instability with respect to prediction on new cases. Coefficients may have very high standard errors and still be statistically significant, possibly, because of implausible high magnitudes. Coefficients may have the wrong sign, or signs that change as another variable enters or is removed from the model. And as p approaches n, the data becomes increasingly collinear. R squared tends to 100%, even when the population predictors are independent. Okay, so we get the prediction of the dependent variable appears to be quite high. Thus, prediction on new cases based on an overfit model may be poor, high prediction error. Okay, before getting into an example, let's just look at this formula here, which is the variance of a particular regression coefficient, the regression coefficient for the gth predictor. Notice here this term 1 minus r squared sub g. So 1 minus r squared sub g is the tolerance of x sub g. And that's computed by regressing that predictor as the dependent variable on all the other predictors and computing the r squared and then 1 minus that. That's the tolerance. So if r squared sub g is equal to 1, that means that predictor can be perfectly predicted from the other predictors. You have perfect collinearity. The extent to which this is close to 1, here the tolerance is going to be low. Okay, so that indicates some problems with collinearity. Here, as n is small, so if we do have something close to 0 here, the variance is going to be infinite. So the variance gets very, very high due to low tolerance for one or more for this predictor. It also gets high if the sample size is small or if the number of predictors gets close to the sample size. Okay, so let's take a simple example. Here we have 6 predictors and a small sample size, 24. So instead of individuals, each case is a car. So we have 24 different cars, car models, and we want to predict the price, the selling price of the car. Now here, this is real data. Price is measured in francs. That dates the example. And the 6 predictors are the cylinder, power, speed, weight, length, and width of the car. Now notice that each of these predictors is highly correlated with price, positively correlated. They're all significant. But each predictor is also highly correlated with the other predictors. Okay. So what happens? Now, if we estimate least squares regression with these data, we get an r squared of 0.85, which suggests quite good prediction. But if we look at the regression coefficients, what we notice immediately is for cylinder, speed, and width, we get negative coefficients, which is unreasonable. If we look at the standard errors, we see quite large standard errors. If we look at the p-value, we see there's one p-value that's significant. That's for power. Now, since this solution is based on a relatively small sample and correlated predictors, it's likely that this model overfits the data. I mentioned that cross-validation is the workhorse here. We will see how to compute the cross-validated r squared. In this example, the cross-validated r squared shrinks to 0.63. And if we requested traditional collinearity statistics, which includes the tolerance, what we would see here is that the predictor with the smallest tolerance is power. And it suggested that in cases where you do have collinearity problems, as in this example, what you should do is eliminate the variable that has the lowest tolerance. So here, it suggests you'd be eliminating the only variable that's significant. Now, what we're going to be talking about are different regularized solutions. This one is based on CCR, correlated component regression. And in that case, we get all positive coefficients. They all turn out to be, again, reasonable, because they're positive here. And the CVR squared is 0.75, so it's higher than the OLS regression solution. So we're going to be relying on cross-validated criteria, cross-validation as the criteria for judging various aspects of a model, including which models perform best. Now, the other thing that we'll be talking about is an optional step-down algorithm. So if we wanted to try to reduce the number of predictors, if there turn out to be extraneous predictors where the regression coefficient was 0, we'd want those to go away. And in the CCR with the step-down algorithm, we end up with 3 predictors, which gives a higher CVR squared. Cross-validated R squared goes up to 0.77. So this would be our final model here, model with 3 predictors. And we'll discuss how to get this. What do I mean by 2 components, etc. Here, cross-validation was based on 10 rounds of 6 folds. So I'll be talking about what that means. Okay, now there's other methods for doing step-down regression or step-up regression. And the most popular way of doing variable selection is with stepwise regression. However, there's many, many problems associated with stepwise regression. And Frank Harrell, who is an expert in stepwise procedures and high-dimensional data regression, this is obtained from his website and his book also. Yields R-squared values that are badly biased to be high, etc. I'll let you look at that. Okay, so the general solution is regularized regression. So what is regularized regression, and what is correlated component regression in particular? So, again, the general solution to this problem is regularization. The simplest way to obtain a regularized solution is to set one or more regression coefficients to 0. However, it's difficult to determine which ones should be set to 0. But I just want to mention that that is a regularization approach. So if we eliminate extraneous predictors, that means the true regression coefficient is 0, we eliminate it. That does not create any unbiasedness, but it reduces the variance. And thus, it reduces the prediction error. So if we can do that, we should. And of course, in traditional regression, we often test if a regression coefficient is statistically significant. We eliminate it if it's not, but in a case like this, where you have near multicollinearity, that might lead you to eliminate most or all of your predictors. So the most popular way of doing regularized regression is known as penalized regression. What happens there is that the magnitudes of the coefficients get restricted, biasing them towards 0. And even though it creates a bias, it reduces the variance. and therefore helps remove the problem. The oldest method is ridge regression, and some newer approaches are lasso and ElasticNet. Lasso has become very popular recently because of its property of sparsity, which means that it not only restricts the magnitudes of coefficients towards zero, but also sets many of them to zero. So it's an approach for variable selection at the same time. And ElasticNet, which is a mixture of lasso and ridge regression. The most popular package for doing these kinds of models is the R package, GLMNet. Now, the other major category of techniques, which with my simulated data perform significantly better than the penalized regression approaches, are known as component dimension reduction approaches. Instead of setting some coefficients to zero or making some restrictions on the predictors, you actually you look at the dimensions and set some higher dimensions to zero, thus reducing variance. Okay, in particular, it's done by replacing the P predictors, which again, where P can be greater than N, replacing the P predictors by K components, where K is less than or equal to P. One way to do this is principal components regression, PCR. That is, you take the predictors, you form principal components, you take the first principal component and you use that, you use the second, you use the third, you continue for a certain number of components, and you just use those, the best components, as the predictors. The problem with that is that principal components does not use the dependent variable at all. So those components, which the first component has maximum variance, the second component has second most variance, that may or may not predict what you're interested in predicting. So it may not predict well. Okay, then we have two other approaches, component approaches, that do utilize the dependent variable. So they do produce good predictions of the dependent variable that you're interested in. Partial least squares regression and correlated component regression. Now, one difference between the two, they're very similar. One difference is that PLS regression is scale dependent, which means that if you standardize the predictors so that they're z-scores, you will get different models than if you use unstandardized predictors. Correlated component regression is scale invariant. It doesn't matter whether you standardize or not. We'll talk a little bit more about that difference shortly. Okay, so the basic idea of the component approaches, and we'll be talking about that now for the remainder of this presentation, is that you use the components rather than the predictors as your inputs. Now, the first component, called S1, is just a linear combination of the predictors. So I'm going to use lambdas to be the loadings for the predictors on the first component. So lambda 1, 1 refers to the loading of predictor 1 on the first component. Okay. The loading of the second predictor on the first component is this. Okay. The second component is also a linear combination of the predictors. Every component is just a linear combination of the predictors. And I use the superscript 2 to distinguish loadings from the second component, from the loadings from the first component. Now, what we do again, suppose we had a two-component model. So we use S1 and S2 as the components. Now, the difference between all of the component approaches is how we get the components. Okay, so we'll be talking about that shortly. But suppose we use some approach for getting the components. So we get the loadings in some way, and we compute the components. We use those as predictors, and we get these component weights. And this leads to the predictions that we're going to use for y hat. Now, how do we get back to getting predictions, to getting the coefficients for the original predictors? Well, it turns out to be very easy. If we just substitute this equation here for S1 in place of S1, and this equation here for S2 in place of S2, and regroup the terms, we can re-express this in terms of the original predictors, where the regression coefficient for x1 is b1 times lambda 1, 1 plus b2 times lambda 1, 2. So that's now we define as beta 1. So more generally, for any given regression coefficient here, that can be obtained as the component weight for the first component times the loading for that predictor on that component, plus the component weight times the loading on the second component. Okay, so notice that we have just this simple expression here for beta G. Now, this applies for any value of K or P, where K, number of components, is less than or equal to P. So in particular, if K is equal to P, we have what I call the saturated model, which gives the same coefficients as standard OLS regression. In other words, regardless of how we get the components, if we take the number of components equal to the number of predictors, and we go through this procedure, what we end up with are, in fact, equivalent to the least squares regression coefficients. And what that means is that least squares, we're not doing any regularization at all. So we're using these 6 terms here in the case of a 6-predictor model. And this will yield the OLS regression coefficient. Now, in the case of K less than P, then we're imposing some regularization. The lower the value of K, the more regularization we're imposing. So we could have a 5-component model, which imposes a little bit of regularization on the 6 predictors. Or we could have 4 components, 3 components, 2 components, or 1 component. 1 component imposing the most amount of regularization. Now let's just look at a simple proof for the claim I made that it's equivalent to least squares regression. Okay, so we have for least squares regression, we have y hat is equal to x times beta hat. This is the least squares coefficient, which are the x prime x inverse, x prime y. Now instead of that, we now have the components. So we have s times gamma hat. Gamma hat are the regression coefficients for the gamma. That's s prime s inverse, s prime y. And just substitute that, and then just some simple rearranging or applying matrix algebra, we end up with the same thing here. So the predictions based on the components, where the number of components is equal to the number of predictors, turns out to give us the same predictions. To impose the assumption that the number of components is equal to the number of predictors, we use this. S is equal to XA, where A is a non-singular matrix. Okay. And so since the predictions are the same, if we then take S and we substitute XA, we see we get Y hat, X, X, beta hat, and we have A gamma hat. So A gamma hat are, in fact, equivalent to the regression coefficients from least squares regression. Okay, so now I'm going to get into the correlated component regression approach. And what we'll see is that when we have K, the number of components, equal to the number of predictors, it gives us the least squares regression. So least squares regression can be estimated as part of CCR, and it's called the saturated CCR model. Now, first I'm going to make some general statements in introducing correlated component regression before giving you the exact algorithm. Now, the first component in CCR, so now the question is, what distinguishes CCR from other methods? It's how the components are computed, so how the loadings are computed. So how are the loadings computed? So first I'm going to give you some general rules about how they're computed, and then I'll show you exactly how they're computed. So it turns out that the first component captures the effects of predictors which have what I call direct effects on the outcome. It's a weighted average of all one predictor effects. I'll define that specifically. The second component, correlated with the first, captures the effects of suppressor variables that improve prediction by removing extraneous variation from one or more of the predictors that have direct effects. I'll be talking more about that. Now, in terms of suppressor variable has zero correlation with the dependent variable. So it has no direct effects on the dependent variable at all, and it will not be captured at all in S1. But such variables, as we'll see, turn out to play a major role in regression and prediction, and may turn out to be the most important variables in the whole model. Often they are, and I'll give you an example of that shortly. So they should not be ignored, and one of the main problems today is that in the case of high-dimensional data, we have so many predictors, some people it's common practice to eliminate suppressor variables, any variable that's uncorrelated with the dependent variable or non-statistically related to the dependent variable before you start the analysis. And that's eliminating the suppressor variables, which could be eliminating the most important variables. And so you're definitely underperforming when you do that. And again, I'll get into more details, give you a specific example of that. That's why the topic of suppressors are an important topic here. Then the role of cross-validation is to judge how many components we should have. So we keep adding more and more components as long as the CVR squared goes up. And we'll see here, again, if we include K is equal to P, that's the CVR squared for the linear regression, OLE, ordinary least squares model. And what we saw before in that first example was that that can be improved upon. And CVR squared is the key to doing that. You can't use just the traditional least R squared because that is maximized by OLS regression. And the more predictors you have, the higher that goes. So you can't use that. You have to use the cross-validated R squared. Then I'll also distinguish prime predictors, which are those having direct effects, from suppressor variables. Those who have their prime predictors have substantial loadings on the first component, while suppressor variables will have very small loadings on the first component, but will have substantial loadings on the second component. Okay, and then we'll get into this variable reduction approach using step-down algorithms. This is an option. so you can do it or not do it. And I'm going to give you a couple examples of when you would do it and when you would not want to do it. Okay. So in practical, there are practical applications where you know your predictors and you don't want to exclude them. Now, the way that the step-down works, and I'll get into that in more detail shortly, at each step, the least important predictor is removed, importance being defined by the absolute value of the standardized regression coefficient. M-fold cross-validation is used in CCR to determine the number of components and the number of predictors. So those K and P are the two tuning parameters. Now, this is an example here with K equal to 2 and P equal to 10. So we have 10 predictors. We have a two-component model. A standard regression would yield an intercept plus 10 components. In correlated component regression with K equal to 2, we get an intercept plus 2 component weights, one weight for each of the two components. And then if we substitute back into the predictors, as I showed you before, we'll get the intercept plus 10 regularized coefficients. So now we get regularized coefficients instead of non-regularized coefficients. Okay, so how do we get the loadings in CCR? Let's look at the first component. How do we get those, what I call direct effects? So we have here is just simply we take the dependent variable and regress it on each predictor one at a time. We take the regression coefficient that we get, that simple regression coefficient, and that's lambda G1. Or we could divide it by the total number of predictors. It really doesn't matter, as I'll show you shortly. We can define it as either lambda G1 or lambda G1 divided by P, the loading. Okay, so then the component is just the sum of those loadings times the predictors. Okay, so that gives the first component. And if we just had a one-component model, we would just take Y and regress it on S1 as the single predictor in the model. We'd compute the B1, the component weight for that component, and we'd get the intercept, and that would give us our predictions. So that's the one-component model. Now, suppose we find that the two-component model improves prediction. CVR squared is higher than the one-component model. What is the two-component model? How's the second component computed? Well, it's very similar to the one-component model, except to get the lambda G now, it's a partial effect, where we take S1, which we already computed. That's the first component that we computed. And we put that in the regression equation as covariate. In other words, it's another predictor. So now we have, for each predictor, xg, one at a time, what we do is we enter that and we do a regression of y on S1 and that predictor. So we now have two predictors in the model. So we compute lambda G2 as the partial regression coefficient controlling for S1. And we use those as the weights for the xg, and that gives us the S2. So then we have S1, which we computed before, and now we have S2 also, and we do least squares regression to get A, B1, and B2, and that gives us the two-component model. the predictions for the two-component model. And as I showed you before, we could also get the regularized regression coefficients for each of the predictors. Okay, now we can continue this to go to 3 components, and in that case, we control for both S1 and S2 as covariates in the model. Otherwise, it's the same thing. So we have S1 capturing the direct effects. S2 captures the effects of suppressor variables, as I've mentioned before. And S3 and higher components can be interpreted as also capturing suppressor effects. Now, so let's look at how we get the number of components. So tuning K. How do we optimize the tuning parameter K? How do we determine the optimal amount of regularization to impose in the model? So case 1 is where we don't want to do any variable reduction. So we're using all predictors that we have in the model. Well, we have an automatic procedure built into the CORExpress program for doing this, determining the optimal K. And what you need to do is specify the maximum value of K. So suppose we had 100 predictors. Okay, suppose we wanted to know what's the best model, but I'm just going to limit to 10 components. Often in practice, we find that 3 components, 4 components, definitely less than 10 components are needed. So even if you have thousands of predictors, you really don't need more than 10 components, and typically between 2 and 6 components. So you specify a maximum number, let's say 10 components. Call that K max. Then the way that this works is that first you estimate the first component, you do a 1-component model, and you get the CVR squared. Now, what is the CVR squared? Well, when you do M-fold cross-validation, you assign cases to one of M folds. So suppose M is 10. You have 10 folds, and you have 100 cases altogether. So the 100 cases are divided into groups of 10, so we have 10 cases in each fold. And then we do this model, eliminating the cases from one of the folds. We estimate the regression coefficients that we get from that model, and we apply that model to the cases that have been omitted. And we set those aside. Those are the predictions that we get for those cases. Then we do the same thing in the second fold. So the second fold, we take those set of 10 cases, and we set them aside, and we estimate the model on the remaining cases, and we get a different set of regression coefficients. We apply those set of regression coefficients to the cases that we set aside. We get predictions for those cases, and we set them aside. We repeat this for all 10 folds. We then combine the information, the predictions on all 10 folds, so we now have all the cases predicted using models where those cases were not used at all to determine the coefficients. And we take those predictions and we correlate with them with the observed values of y to get r. We square it to get r squared. So that's the CVR squared, cross-validated r squared. So we can do that for a 1-component model. We can do it for a 2-component model, 3-component, see whether it's increasing, how high it goes. And then the one for which the CV performance is best, highest CVR squared, that gives us the K. Okay, so now let's actually make this concrete, I will go to CORExpress program, and what I'll do is take price as the dependent variable for this car data, and then as far as the predictors, I'll select all 6 predictors. As far as maximum number of components, I'll say 6. Now, if it's all 6 in there, then we have the least squares solution. I'll select automatic. I'll select the linear regression model. Later, we'll look at linear discriminant analysis. And then, as far as the cross-validation goes, say use it, and I'll take 10 rounds of 6 folds. Okay, now how did I choose 6? Well, I mentioned that there's 24 cases here. So what we'd like to do when we assign cases to folds is have exactly the same number of cases in each fold whenever possible. So 24 is evenly divided 6 times 4 or 8 times 3. And typically we'd want to choose the number of folds to be between 5 and 10. So here I pick 6 folds. So each of the 6 folds would have exactly 24 cases. Now we say estimate. And what we see here is that with 6 components, this is the least squares solution. That's where I got my CVR squared of 0.63. Now we start imposing regularization. We see that the 5-component model improves a little bit. 4-component improves further. 3-component improves further. So we're imposing quite a bit of regularization. And then 2 components really improves quite a bit. And 1 is about the same, slightly less. So we take 2 components as the optimal value for K. And what we see here is that here with 2 components, we have 0.75. So that's the cross-validation R squared, CVR squared. Now, R squared in the training sample is 0.8189, higher than that. And I mentioned before that R squared based on OLS regression was something like 0.85. So OLS maximizes the R squared. We get a maximum of 0.85, but a better solution gives us an R squared of only 0.82 because it has a higher CVR squared. So it's going to validate better on new cars when we try to predict based on new cars. Here are the coefficients for cylinder, power, speed, weight, length, and width. See that they're all positive. These are, in fact, the loadings from the first component for each of the predictors and the loadings for the second component. And these are the standardized values. These are more easy to interpret. But the key is that when we did 6 components, we get a CVR squared of 0.63. And when we just do 2 components, it goes way up to about 0.75. We also get a standard error for this number, which comes from the fact that I repeated this 10 times. Now suppose I only did it 1 time. Okay, I still got 2 components as my optimal solution. So the results are exactly the same. But these numbers now are slightly different because it's only based on 1 round of 6 folds. In other words, I'm taking all 24 cases and I'm assigning them to 6 folds at random. And I can do that just 1 time. I get 1 set of assignments. I could do it 2 times. I can now randomly assign them a 2nd time and repeat the process. I can do it a 3rd time. I could do it 10 times. If I did it 10 times, or as long as I'm doing it more than one time, I can then get these numbers for every round, and I can compute a mean, and that's what's reported here, and I can get a standard deviation, and that gives me the standard error. So when I do 10 folds, I then get another set of numbers, which are the standard errors here. Okay, so that's the basic idea. Now we go back to the presentation, and in practice, candidate predictor variables may include extraneous or completely irrelevant predictors. In other words, population coefficients equal 0. Prediction can be improved upon in such cases by excluding such predictors, resulting in a sparse model. Some coefficients are set to 0. So here we have a graphical depiction of two predictors, x1 and x2. This is the dependent variable, y, and you can see both are correlated with y. In this case here, we have a third predictor, which is irrelevant. Okay, it is not correlated at all with y, and it's also not correlated with either of the x's. So clearly, if we had such predictors, we would want to eliminate them, because to include them, you get a regression coefficient estimate for that adds nothing but error. So you get additional error. And so we can reduce prediction error by removing that and get more efficient estimates of the predictors that are in the model. So the question is, how do we know when, in fact, we have such predictors that should be omitted? Okay, so the way that the step-down algorithm is implemented in correlated component regression is for a given number of components, what we do is we did that first with all predictors in the model. And then we eliminate the least important predictor in that model, where importance is quantified by the absolute value of the variable standardized coefficient. This is just the usual formula for standardized coefficient. This is an unstandardized coefficient. This is the standard deviation of the predictor variable. This is the standard deviation of the dependent variable. This gives us the standardized coefficient. This is the unstandardized coefficient. For example, in SPSS, this is reported as beta. This is B. That's just terminology. Okay, so for example, suppose we had a two-component model. What we do is we standardized the coefficients for the two-component model, and we then see which one is closest to 0. The absolute value is closest to 0. We then eliminate that predictor and then repeat the steps of the CCR estimation algorithm on the reduced set of predictors. That is, we divided everybody into, say, 6 folds. Okay, so the first time we did this, we compute CVR squared, and the predictions that we're getting now have different coefficients for each of these subfolds, where we have the analysis sample after we eliminated the fold. Now, what we do is, in each time we estimated, now we do this standardization and we eliminate the predictor that's least important. And then we apply the results of that model to the omitted folds. So when we're doing this with respect to step-down, when we apply the predictions, when we apply the regression coefficients to the omitted folds, we might now have predictor X2 eliminated in one situation, but in another situation where when we eliminated, say, the fourth fold, those cases that were in the fourth fold, when we standardized, we may have picked predictor X2 to eliminate. So we get the predictions, the regression coefficients based on those predictors, and we apply that to the omitted folds. And that's critical to do it that way, because then at the end, when we compute the CVR squared, that gives us a valid measurement for the CVR squared for the model with fewer predictors. Okay, so when we look at that, it's a little complicated. So we look at it with CORExpress, it'll become more clear, become concrete. Now, in practice, for large P, more than one predictor can be eliminated at a time. So by default, what we do is eliminate 1% or pick a percent of the predictors that are eliminated at a time until P is less than 100, at which time we eliminate one predictor at a time. And that process can continue until one predictor remains. Finally, one other technical issue here. For P equal to K, the model becomes saturated as equivalent to the traditional least squares regression model. But we know that K cannot be greater than P. K is always less than or equal to P. So when we're reducing the number of predictors, once we get to K predictors, then what we have to do is also reduce K so that we maintain the saturated model. In other words, suppose we had K equal to 4, so when we step down to 3 predictors, we reduce K so K equals 3. And that's similar to what's done in stepwise exclusion, in traditional stepwise regression. Basically, you're maintaining the saturated model at each step. So that's done automatically by the program. Okay, so let's actually look at that now. And we go here and we now say we have 2 components. We turn off automatic and we go to step down. Perform step down regression. Use 10 rounds of 6 folds again. And what we see here is that we now have just 3 predictors. Okay, so we see is that we went to 6 predictors, down to 5, down to 4. Then we went down to 3. We get higher CVR squared, and that's where it's maximized. Okay. Now, let's see, we're going to take a break in about 2 minutes. And I just got one question in here. Let me just address this question. Are S1 and S2 regression models? Okay, so let me go back to that slide. So we go back to the notation again. Okay, so S1 and S2 are components. So how do you get components? Again, what we decide, first we do a one-component model that just has S1 in it. and then we do a two-component model, which has two components in it. So this is the regression model here that has two components in it. S1 and S2, we get regression model with two components. That's called a two-component model. If there was just one component, then we'd have the one-component regression model. M-fold cross-validation is used to decide how many components are going to be included in the model. Okay, so what we're going to do now is take a 5-minute break, and before we take the break, well, actually, let me just finish this one slide here, which summarizes how we determine that there are three predictors. And we saw that originally we selected two components as the number of components. We may also want to try three components and see if we get a better solution when we use step down. So maybe three predictors with three components does better. I've done that, and it turns out two components is the best. So we want to optimize the number of components, K and P, number of predictors. Now here we also have this additional output which keeps track of the 10 rounds of M-folds that were done. And we see that the first round, 3 predictors was optimal, then 6, 3, 3, 3, 2, 2. So this is a nice summary, supplemental information, and also it counts up in this round where there were 3 predictors, how many times was power included among the 3 predictors? How many times was weight included, etc. So we could see here that overall power was included 60 times, weight 59, speed 27, cylinder 23. So it gives us another measure of a variable importance. So I'm going to finish this, address any additional questions, and then we'll go on to the first example with high dimensional data.